What if I told you that, according to the most fundamental, unbreakable laws of physics, you shouldn't be here? That this world, this reality, everything you've ever known, seen, or touched, is a cosmic glitch, a 1 in a billion rounding error in the mathematics of creation. It sounds like the opening of a science fiction film, but it is the single greatest mystery of our existence. We live in a universe that, by all accounts, should have instantly destroyed itself, leaving behind nothing but a silent, empty sea of light. So why didn't it? The answer lies with a substance so strange, so volatile and so powerful, it pushes the limits of our imagination. A perfect mirror to our reality, called antimatter. And the story of this cosmic twin is the story of us, the impossible survivors of a war that was fought and won in the first trillionth of a second of time. Let's begin with a concept that sounds deceptively simple. For every single particle that makes up you, me, and the entire visible cosmos, there is a twin, an antiparticle. The electron, with its negative charge, has a twin called the positron, identical in every way, same mass, same spin, but with a positive charge. The powerful proton that sits at the heart of every atom has its own dark twin, the antiproton, with a negative charge. This perfect, almost poetic symmetry was first predicted not in a laboratory, but in the elegant equations of a physicist named Paul Dirac, back in 1928. He was trying to merge the wild new world of quantum mechanics with Einstein's theory of special relativity, and his mathematics kept spitting out a strange solution. A particle that behaved just like an electron, but with an opposite charge. He had discovered antimatter on paper years before it was ever seen in the real world. Now, this is where the story takes a dramatic turn. When a particle of matter meets its antiparticle twin, they don't just collide, they annihilate. They vanish in a flash of pure energy, more brilliant and more violent than any other process known to science. This isn't like a chemical reaction, where atoms are just rearranged. This is total conversion of mass into energy, following Einstein's legendary equation, E=mc2, with 100% efficiency. To put that into perspective, a nuclear bomb is considered terrifyingly powerful. Yet it only converts about 1% of its nuclear fuel into destructive energy. A matter-antimatter reaction converts 100%. Let's try to imagine that power. Take a single gram of antimatter, an amount smaller than a raisin, and let it touch 1 gram of regular matter. The resulting explosion would release the energy of 43 megatons of TNT, more than twice the power of the Tsar Bomba, the largest nuclear weapon ever detonated. A single gram. This isn't just a reaction. It's the universe's ultimate reset button, the most potent and dangerous process we have ever conceived. It's the physical embodiment of two perfect opposites, meeting and returning to the pure, raw energy from which they were born. So where is this exotic, unbelievably explosive substance? You might imagine it locked away in the world's most advanced laboratories, something out of a Dan Brown novel. And you'd be right, we'll get to that. But the truth is far, far stranger. Antimatter is not just in some far-off lab. It's being created right now, all around you, and even inside of you. Every second, our planet is bombarded by high-energy particles from deep space called cosmic rays. When these cosmic bullets slam into the upper atmosphere, the sheer force of the impact creates tiny pairs of matter and antimatter particles in a constant, invisible fireworks show. Lightning strikes, in their violent release of energy, are powerful enough to forge positrons, the antimatter twins of electrons. Even the enigmatic jets firing from the poles of black holes are thought to be colossal antimatter factories. The universe, it seems, is constantly making this stuff. But it gets even more personal. You might have had a banana with your breakfast this morning. Bananas are famously rich in potassium, and a tiny fraction of all potassium is an isotope called potassium-40, which is naturally radioactive. As potassium-40 decays inside your body, it occasionally spits out a positron. That's right. For a fleeting moment, your own body becomes a source of antimatter. It's a tiny amount, gone in a flash, as it finds a nearby electron to annihilate with. But it's there. From the silent decay of an element in a piece of fruit to the fury of a cosmic storm, the universe is constantly whispering its mirror image into existence, hiding it in plain sight before it vanishes again. This brings us to the heart of the great mystery, the question that keeps physicists awake at night. The Big Bang, our theory of creation, states that energy can transform into matter. But there's a catch, a fundamental law that must be obeyed. You can't create a particle without also creating its antiparticle. Energy must always birth matter, and antimatter in perfectly equal amounts. So in that first fiery moment of creation, for every single quark that was forged, an anti-quark must have been born. For every electron, a positron. A perfect, balanced 50-50 split. Now think about what we just learned about annihilation. If the early universe was a dense, hot soup of equal parts matter and antimatter, they should have found each other almost instantly. The entire cosmos should have annihilated itself in a fraction of a second, leaving behind a universe filled with nothing but pure energy, a vast, featureless sea of light. No stars, no galaxies, no planets, and certainly no us. Yet here we are. We exist. The chair you're sitting on, the air you're breathing, the stars in the night sky, it's all made of matter. There is no significant amount of antimatter to be found. And this is the cosmic crime scene. Where did all the antimatter go? The only explanation, bizarre as it sounds, is that the universe cheated. In the very first moments of its existence, the laws of physics must have had a slight, almost imperceptible bias toward matter. For every billion matter-antimatter pairs that met and annihilated each other, one single solitary particle of matter was somehow left over. Think about that. You, me, and everything we have ever known are the leftovers. We are the scrap, the 1 in a billion rounding error from that primordial annihilation. We are the survivors of a universal war that was over before the first second of time had even passed. Our entire existence is owed to a fundamental imbalance, a tiny flaw in the perfect symmetry of creation. But what if the antimatter isn't gone? What if it just went somewhere else? This is the tantalizing possibility that drives one of the greatest searches in modern astronomy. What if, somewhere out there in the vast unexplored darkness of the cosmos, entire galaxies were built from the other side of the mirror? Imagine anti-stars, burning anti-hydrogen and anti-helium, with anti-planets orbiting them, perhaps even with anti-life looking up at their anti-sky. From our distant perspective, such a galaxy would be completely invisible to us. Why? Because an anti-star would produce anti-photons, but photons are their own antiparticle. The light it emits would be identical to the light from our own stars. We couldn't tell the difference just by looking. So how could we ever find it? There's only one way: look for the evidence of a cataclysm. If a galaxy made of matter were to collide with a galaxy made of antimatter, the resulting annihilation event would be the most spectacular and violent spectacle in the entire universe. The boundary where they met would erupt in a fountain of high-energy gamma rays, a unique signature of matter-antimatter annihilation. This cosmic battlefront would be so powerful, it would make a supernova look like a flickering candle. This is exactly what astronomers are searching for. High above our atmosphere, aboard the International Space Station, a sophisticated particle detector called the Alpha Magnetic Spectrometer, or AMS-02, is patiently sniffing the cosmic winds. Its primary mission is to search for the telltale signs of this missing antimatter. Finding just a single nucleus of anti-helium, for example, would be a smoking gun. A simple antiproton could be created in a cosmic ray collision, but forming something as complex as an anti-helium nucleus would require an environment like an anti-star. And here's the thrilling part. In the last few years, the AMS-02 experiment has reported the potential detection of a handful of these anti-helium nuclei. The data is still being analyzed, and scientists are being incredibly cautious, but if these signals are confirmed, it would be revolutionary. It would mean that somewhere out there, the other half of our universe is not gone. It's just been hiding. This all raises a very practical question. If antimatter is so incredibly volatile that it annihilates on contact with anything, the air, a metal container, anything, how on earth do scientists even begin to study it? How do you hold on to something when you can't let it touch the container? The answer is something straight out of science fiction. You build a cage made of nothing. Scientists use powerful, complex arrangements of magnetic and electric fields to create an invisible container known as a magnetic bottle, or a penning trap. Because antiparticles have an opposite charge to their matter counterparts, they can be manipulated by these fields. The fields are precisely tuned to push the antiparticles away from the walls of the chamber, forcing them to hover in a near-perfect vacuum, suspended in the middle of nothing, touching nothing. It is an unbelievably delicate and difficult process. For decades, scientists could only create and hold on to antimatter for fractions of a second before it was lost. But the technology has advanced at an incredible pace. It's also staggeringly expensive. Based on the energy and infrastructure required at places like CERN, the European Organization for Nuclear Research, it's estimated that producing a single gram of antimatter would cost an astronomical $62.5 trillion, making it by far the most expensive substance on Earth. There isn't enough money on the entire planet to buy a gram. But for physicists, every single anti-atom they can create and hold is priceless, because each one holds a potential clue to the deepest secrets of our existence. As physicists delved deeper into the strange relationship between matter and antimatter, they uncovered a truth about reality that is as profound as it is bizarre. On the surface, our universe seems unbalanced, with its preference for matter. But underneath it all, there appears to be a deeper, more fundamental symmetry that is never, ever broken. It's called CPT symmetry. The letters C, P, and T stand for three fundamental operations. C stands for charge conjugation. That's the act of swapping a particle for its antiparticle. P stands for parity, which is like reflecting the particle in a mirror, reversing its spatial coordinates. And T stands for time reversal, which means running the particles' interactions backward in time. Individually, some physical laws are violated. We've seen that the universe seems to violate C symmetry because it chose matter over antimatter. But the incredible discovery was this. When you perform all three operations at once, swap the particle for its antiparticle, flip it in a mirror, and run it backward in time, the laws of physics snap back into perfect balance. They remain completely unchanged. It's as if you have a movie of a particle interaction. If you create a new movie where every particle is an antiparticle, the scene is mirror-imaged, and you play it in reverse, that new movie will be perfectly valid and indistinguishable from a real physical process. This unbreakable CPT symmetry suggests something extraordinary. It hints that matter and antimatter aren't truly separate things. They are two faces of a single, deeper reality, inextricably linked through space, charge, and even time itself. They are reflections in a cosmic mirror that is far more complex and elegant than we ever imagined. This idea of a deep connection through time led one of the 20th century's most brilliant physicists, Richard Feynman, to propose a truly mind-bending idea. What if an antiparticle isn't a different particle at all? What if a positron is simply an electron that is moving backward in time? Think about it from our perspective, as beings who perceive time flowing in one direction. If an electron were traveling from the future into the past, its properties would appear reversed to us. A particle with a negative charge moving backward in time is mathematically identical to a particle with a positive charge moving forward in time. It would look and behave exactly like a positron. In this stunningly elegant view, the act of annihilation isn't the destruction of two separate particles. Instead, it's a point in space-time where a single particle, let's say an electron, is traveling along from the past into the future. At the moment of annihilation, it interacts with a photon, and this interaction is so powerful that it literally reverses its direction in time, and it starts traveling backward into the past. From our forward-looking perspective, it would appear as if an electron moving forward and a positron arriving from the future met and vanished into a flash of light. In reality, it was one particle performing a U-turn in the fourth dimension. This idea, while difficult to wrap our heads around, beautifully preserves the symmetries of physics and suggests a reality where the past, present, and future are far more interconnected than we experience. If the solutions so far haven't stretched your brain enough, buckle up, because the theories get even wilder. To solve the mystery of the missing antimatter, some physicists have proposed a beautifully simple, if untestable idea. What if our universe wasn't born alone? What if the Big Bang created two universes, a matter universe, ours, and a mirror anti-universe, connected only at the moment of their birth? This neatly solves the asymmetry problem. The antimatter isn't missing, it's just in a parallel reality that we can never access. But there's another idea, one that is actually testable. What if antimatter has anti-gravity? We assume that gravity pulls on everything, that it's a property of mass and energy. But what if the charge that gravity sees is not mass, but something else? What if antimatter, instead of falling down, falls up? If this were true, it would provide a stunning explanation for the cosmic imbalance. In the dense, chaotic early universe, as matter began to clump together under its own gravity to form the seeds of galaxies, antimatter would have been gravitationally repelled. It would have been pushed away from the matter, expelled into the vast, empty voids between the galactic superclusters. In this scenario, the missing antimatter wasn't destroyed. It was simply banished, hidden away in the cosmic badlands, where it remains invisible to us today. For decades, this was pure speculation. But now, as we'll see, we finally have the tools to find out if it's true. All of this talk of cosmic mysteries and mind-bending physics might make antimatter seem like a purely theoretical curiosity. But it's not. In fact, this exotic substance is already being used in our world to save lives. If you or someone you know has ever had a PET scan in a hospital, you've witnessed the power of antimatter firsthand. PET stands for positron emission tomography. Here's how it works. Doctors inject a patient with a special sugar molecule, like glucose, that has been tagged with a radioactive isotope that emits positrons. Cancerous tumors are incredibly hungry for energy and metabolize sugar at a much higher rate than healthy tissue. As this radioactive sugar accumulates in a tumor, the positrons are released. They travel only a millimeter or two before they meet an electron in a nearby cell and annihilate. This annihilation releases a pair of high-energy gamma photons that shoot off in precisely opposite directions. A ring of detectors around the patient registers these pairs of photons and can trace them back to their exact point of origin. The result is a stunningly detailed 3D map of the metabolic activity in the body, showing doctors exactly where a tumor is and how active it is. It is a medical miracle, powered by the ghost in the mirror. And the future holds even more promise. Scientists are developing new forms of cancer therapy using beams of antiprotons. The idea is to target a tumor with incredible precision. Unlike radiation, which damages tissue all along its path, an antiproton beam would deposit most of its destructive energy at the very end of its journey, right inside the tumor, where it annihilates, destroying the cancerous cells from within while sparing the healthy tissue around it. And then there's the ultimate dream: interstellar travel. A pure antimatter-powered rocket remains far beyond our current capabilities. But a more plausible design, known as an antimatter catalyzed fusion rocket, is already being studied. This would use a tiny amount of antimatter, mere micrograms, as a sort of spark plug to ignite a powerful fusion reaction in a small pellet of fuel. Such an engine could theoretically propel a spacecraft to a significant fraction of the speed of light, allowing us to reach nearby stars within a human lifetime. Antimatter could one day be the key that unlocks the galaxy. For most of the 20th century, scientists could only create individual antiparticles, a positron here, an antiproton there. They were like having individual bricks but no way to build a house. The dream was to assemble these pieces into a complete anti-atom, the first true building block of the mirror world. That monumental leap happened in 1995 at CERN. For the first time in history, researchers successfully took antiprotons and combined them with positrons to create 9 atoms of antihydrogen. This was an achievement of breathtaking complexity. It was like trying to build a perfect replica of a house using materials that you know will explode violently if they ever touch the original. These first anti-atoms were incredibly fragile and existed for only about 40 nanoseconds before they were annihilated. But in that fleeting moment, they proved something profound: that the mirror world is real and follows the same rules as our own. An antiproton and a positron can indeed combine to form an anti-atom, just as their matter counterparts do. This breakthrough opened the floodgates. It moved the study of antimatter from the realm of individual particles to the realm of anti-chemistry. It meant that we could finally begin to ask the deepest questions about antimatter's nature, by studying it not as a collection of loose parts, but as a complete functioning system, a true reflection of the simplest atom in our own universe. Now that we can create and, more importantly, hold on to anti-atoms for extended periods, we can finally perform the experiment that was once pure fantasy. We can test whether antimatter falls up or down. At CERN, a dedicated experiment called Alpha G, the G stands for gravity, was built specifically for this purpose. The concept is simple, but the execution is one of the most difficult experiments ever devised. Scientists create a cloud of antihydrogen atoms and trap them in their magnetic bottle. Then, very carefully, they switch off the magnetic fields and release the anti-atoms, letting them fall. Detectors at the top and bottom of the chamber then watch to see where the anti-atoms go before they hit the walls and annihilate. If antimatter has anti-gravity, they should all drift upward. If it behaves like normal matter, they should fall down. For years, the world waited for the result, and in late 2023, the Alpha Collaboration published their groundbreaking findings. The answer? Antimatter falls down. In their experiment, they observed that roughly 80% of the released anti-hydrogen atoms annihilated on the bottom detector, a result perfectly consistent with how normal hydrogen atoms would behave under the influence of Earth's gravity. This was both a triumph and a bit of a disappointment. It confirmed a core prediction of Einstein's theory of general relativity, that gravity should affect matter and antimatter in the same way. But it also closed the door on the elegant theory that antimatter was simply pushed into the cosmic voids by anti-gravity. The result was a monumental achievement in experimental physics, but it also deepened the original mystery. If antimatter behaves just like matter, where did it all go? With the gravity question provisionally settled, the next frontier is already in sight. We've moved from antiparticles to anti-atoms. The next logical step is to create anti-molecules. Imagine creating anti-water, H2O, but with 2 anti-hydrogen atoms and 1 anti-oxygen atom, or anti-methane. This is the dawn of anti-chemistry, the exploration of an entire parallel periodic table. By studying how anti-atoms bond and interact, we can test whether the forces that govern chemistry in our world are perfectly mirrored in the anti-world. At the same time, experiments are becoming so incredibly precise that they are searching for the tiniest cracks in the mirror. While we now know that antimatter falls down, The alpha experiment's measurement had a margin of error of about 20%. Future experiments will refine this measurement, looking for even a minuscule difference in the gravitational acceleration between matter and antimatter. Finding even a 0.001% difference would be a Nobel Prize-winning discovery. Such a tiny crack in the perfect symmetry between matter and antimatter could be the key to everything. It could be the clue that finally explains the cosmic imbalance, the reason why that 1 in a billion particle of matter was left over after the Big Bang. Some theories even speculate that a subtle difference in how antimatter behaves could be linked to dark energy, the mysterious force that is causing the expansion of our universe to accelerate. The answers to the biggest questions in cosmology may lie in these ultra-precise measurements of matter's elusive twin. As we push the boundaries of what we can measure, we also need to push the boundaries of how we think about reality itself. String theory, one of the most ambitious and controversial ideas in modern physics, suggests that our universe is not limited to the 3 spatial dimensions we experience. It proposes that there may be many more hidden dimensions, curled up so small that we can never perceive them. In this framework, the relationship between matter and antimatter could be even stranger than we thought. What if they are not different particles at all? What if a particle and its antiparticle are the very same entity, just viewed from different dimensional perspectives? Imagine a coin. From one side, you see heads. From the other, you see tails. It's the same coin, but your perspective determines what you see. Similarly, a particle vibrating in these higher dimensions might present one face to us as matter, and another as antimatter. If this were true, it would mean the missing antimatter isn't gone. It's simply hidden. It exists right alongside us, but in a higher dimension that we are completely blind to. It would be the ultimate cosmic illusion, a universe of antimatter occupying the same space as our own, forever inaccessible and unseen. Taking this idea of a hidden reality one step further leads to one of the most stunning hypotheses in all of science. For decades, astronomers have been grappling with another profound mystery: dark matter. We can see its gravitational effects everywhere. It's the invisible glue that holds galaxies together and keeps them from flying apart. We know it makes up about 85% of all the matter in the universe, but we have no idea what it is. Now let's connect the dots. We have a universe missing its antimatter. We have a universe filled with some mysterious, invisible, dark matter that only interacts with our world through gravity. What if these two mysteries are actually two sides of the same coin? Some theories propose the existence of a mirror matter universe, a parallel world existing alongside our own, complete with its own set of mirror particles and mirror forces. This world would be completely invisible to us. We couldn't see it, touch it, or interact with it in any way, with one exception: gravity. Gravity, being a curvature of space-time itself, would affect both universes. This has led to an incredible idea. What if the dark matter we've been searching for is simply the ordinary matter of that mirror world? We've been hunting for some new, exotic particle when the answer could be an entire parallel reality, overlapping with our own, its gravitational influence bleeding through, forever hidden from our view. Back here on Earth, at facilities like CERN's anti-proton decelerator, scientists are getting down to the hard work of testing these incredible ideas. They are not just creating antimatter, they are recreating the extreme conditions of the early universe in miniature. By slowing antiparticles down to incredibly low energies and trapping them, they can measure their fundamental properties, mass, charge, magnetic moment, with a precision that was once unimaginable. So far, every single experiment has confirmed that antimatter is a perfect mirror of matter. The charge-to-mass ratio of an antiproton, for instance, has been measured to be identical to that of a proton to within an astonishing 16 parts per trillion. The mirror, as far as we can tell, is flawless. But these tests are a double-edged sword. On one hand, They confirm the beautiful symmetry at the heart of our physical theories. On the other, they make the mystery of the missing antimatter even more frustrating. If matter and antimatter are perfect twins in every way we can measure, why did the universe choose one over the other? These experiments are now pushing the boundaries of detection, searching for the slightest hint of a violation, a tiny crack in the mirror that could finally point to the new physics that must exist to explain our own existence. The very fact that we are here to ask these questions forces us to confront an even deeper, more philosophical possibility. The anthropic principle is the idea that the universe must have the properties we observe, because if it had different properties, we wouldn't be here to observe them. For example, if the force of gravity were slightly different, stars wouldn't have formed, and life would be impossible. It's a sort of cosmic selection bias. But what if it's more than that? What if consciousness is not just an accidental byproduct of complex chemistry on a lucky planet? What if it is a fundamental and integral part of reality itself? In the strange world of quantum mechanics, the act of observation can collapse a wave of possibilities into a single, concrete reality. Before it's observed, a particle can be in many states at once. After observation, it's in only one. Perhaps, in the very first moments of the universe, reality itself was in a quantum superposition, a state of being both a matter-dominated universe and an antimatter-dominated universe simultaneously. What if the emergence of the first conscious observers, us, is what forced the universe to choose? Perhaps the act of observation is what solidified one of these quantum possibilities, turning it into the concrete, matter-filled reality we experience today. It's a radical, untestable idea, but it speaks to the profound mystery of a universe that seems to have given rise to beings capable of understanding it. The pace of discovery in this field is breathtaking. Recently, scientists at CERN achieved another major breakthrough, extending their ability to trap anti-atoms from just over a second to over 16 minutes, 1,000 seconds. In the world of antimatter research, 16 minutes is an eternity. This incredible leap allows for far more detailed and precise experiments, confirming nature's perfect symmetry with ever greater certainty. At the same time, this relentless confirmation of symmetry has inspired even more creative theories. A radical new idea has emerged that attempts to solve the mysteries of both dark matter and the missing antimatter in one elegant stroke. It's called the shadow sector theory. What if the Big Bang's cataclysmic annihilation event wasn't the end of the story? What if it created a kind of shock wave that ripped open a pathway to a parallel, shadow universe, and all the antimatter fled into it? This shadow antimatter would exist in its own sector of reality, with its own forces, invisible to us. But, like the mirror matter theory, it would still have gravity. It would behave, from our perspective, exactly like the dark matter we observe today. This theory provides a dynamic explanation for how the separation happened and elegantly ties together two of the biggest puzzles in cosmology. The missing half of our universe might not be in a distant galaxy. It might be right here, in a shadow world, its gravitational ghost shaping the cosmos we see. Looking forward, the future of antimatter isn't just about cosmic discovery. It's about the potential for human transformation. We may not be building pure antimatter drives for our starships anytime soon, given the production cost and challenges. But the more practical, antimatter-catalyzed fusion drives are a serious possibility for the future of space exploration. Here on Earth, the implications are just as profound. If we could ever master this technology, even on a small scale, it could lead to revolutionary new power sources. Imagine compact energy plants that could power entire cities with a few pellets of fuel, producing limitless clean energy with no carbon emissions and no long-lived radioactive waste. It could be the ultimate solution to climate change, providing the energy needed to lift all of humanity out of poverty and ensuring the long-term survival of our civilization by allowing us to sustainably manage our planet and eventually expand beyond it. Antimatter, the substance that could have destroyed the universe, might ironically be the key to saving it. Ultimately, the journey into the world of antimatter has completely shattered our old classical view of reality. We once thought of space as an empty box and particles as tiny, solid balls. We now know that this is wrong. Space is not empty. It is fizzing with quantum fields. And particles are not solid. They are merely vibrations or excitations in these fields. This has led to a revolutionary and profound idea. What if the universe, at its most fundamental level, is not made of matter or energy but of information? If you strip everything else away, what you're left with are quantum bits of information, governed by a set of rules, the laws of physics. In this paradigm, consciousness might not be a strange, emergent property that only happens in biological brains. It could be an intrinsic property of the cosmos itself, the universe's way of processing its own information. In this view, you are not just a collection of particles living in the universe. You are the universe. You are a piece of the cosmos that has evolved to the point where it can look back upon itself, process the information it's made of, and become self-aware. You are the universe asking what it is. And so, we are left standing before a profound and beautiful truth. Our entire existence, every star, every planet, every living creature, every conscious thought, is the result of a tiny, 1 in a billion imperfection at the very dawn of time. Antimatter is the ghost in the mirror that reminds us of this fact. It shows us the silent, empty universe of pure light that could have been, and in doing so, reveals the sheer, improbable miracle of the universe that is. We are the children of that cosmic imbalance, and in our quest to understand antimatter, we are fulfilling a remarkable destiny. We are the universe looking at its own reflection, seeking to understand the flaw that allowed it to exist, and asking the ultimate question: why is there something rather than nothing? What we've learned from this journey is a lesson that applies not just to physics, but to our own lives. We learn that perfect symmetry, while beautiful, can also be sterile and empty. It was an imperfection, a tiny break from the pattern, that allowed for all the complexity and beauty we see around us. It teaches us to perhaps value the imperfections in our own lives, the small deviations from the norm that make us unique and allow for growth and creativity. The relentless, decades-long hunt for antimatter also teaches us about the power of human curiosity. It's a testament to our innate need to ask why, and to follow the evidence wherever it leads, no matter how strange or counterintuitive the destination. It reminds us that the reality we perceive with our senses is only a tiny sliver of the true underlying nature of things, and that there are always deeper layers to uncover if we only have the courage to look. Finally, the story of antimatter is a story of perspective. The idea that a particle is its own antiparticle moving backward in time shows us that two things that seem like polar opposites can, in fact, be two faces of the same single reality. It's a powerful metaphor for finding connection and unity, where we once saw only division. So, as we go about our days, perhaps we can carry a piece of this cosmic wonder with us. We can appreciate the beautiful imperfection of our world. We can nurture our own curiosity. And we can remember that there is always more to reality than meets the eye. It's a truly humbling thought, isn't it? That we are the result of a glitch in creation. It leaves me with so many questions. What do you think really happened to all the antimatter? Does the idea of a mirror universe existing right alongside our own excite you or unnerve you? And what do you think humanity's future with this incredible substance will look like? I would love to hear your thoughts in the comments below. Stay curious, stay questioning, and above all, stay healthy. And if you enjoyed this journey to the other side of the mirror, please don't forget to like this video, share it with someone who loves a good mystery, and subscribe to the channel for more explorations into the cosmos. Thank you for watching.